Hello, hey, my name is James Sanders. Welcome everybody to the AI Coffee Chats podcast. Today I'm talking with Aaron Epel, who is currently a senior data scientist at STEM. Aaron and I both worked at IHS Energy, so we share some history and some past life in the energy sector. And IHS Energy is now a part of the Standard & Poor's conglomerate. So that's definitely big tech there. We also collaborated on a day-ahead electric demand forecasting project. I'll leave a link to that in the notes as well. We compared the performance of several deep learning algorithms and calculated the financial impact on a network operator, basically on a grid operator. And as I said, I'll put a link to all that stuff in the show notes. Today, what am I drinking? Well, it's a bit later in the day than normal, so I'm actually not having coffee today. I'm having a little bit of white wine. And what's the poison of choice? It's a very classy box of Pinot Grigio. Very high value, I would say, not particularly strong on the quality side, but very good value. Welcome, Aaron. Hi. What are you drinking today?
Hey, James, it's great to be invited to join you on your podcast. Today, I'm actually going with some tea, some chamomile tea, believe it or not. I've had a little bit of a manic Monday, and this is good for unwinding a little bit and getting into the groove after a long but exciting day.
Good for you. All right. Well, why don't you get us kicked off, Aaron? Tell us a little bit about yourself, your background, and we'll sort of take it from there.
Yeah, absolutely. So, so James, you and I were colleagues at IHS Energy a while back.
It's a long
time
ago.
Since then, I went deeper into the data science and machine learning rabbit hole, specifically for the energy sector, which had gotten me pretty excited about the applications there. I spent a little over 5 years at Nexterra Energy, working on the Nexterra Analytics Energy. Excuse me, that chamomile still needs to kick in. The Nexterra Energy Analytics team, and then at Florida Power and Light for part of that. And most recently, I've been at STEM for almost 2 years now, working on performance engineering for the battery energy storage system and solar plus storage fleet. And that's been fascinating. Energy storage is such an interesting area where we're seeing lots of neat data science applications, making this practical, right, for today's grid and for today's
it's such a hot area right now. Like it's really interesting, and I think we're going to probably just as a bit of foreshadowing, I think Aaron and I might be going to do another podcast specifically on some use cases around charging and charging stations and AI and ML to optimize operations there. So that's really exciting. But why, or how was it that you originally got interested in AI and ML for the energy sector?
So it's funny, actually, my supervillain origin story starts at IHS. I remember working on a project around generating atlases for hazardous chemical flows on state highways.
Okay.
And I had been doing some studying in my spare time on, well, how might we optimize this, right? Rather than just producing the atlas, could we also recommend where's the best place to put your first responder stations? And I remember one of my mentors at the time was saying, if you're interested in these problems, you need to go back to school, right? And study this more formally. So I went back for my master's degree in operations research. And as part of that, got exposed to a lot of what was emerging in sort of applications of deep learning. And just got bitten by the bug.
Yeah,
well, start focusing more and more on applied statistics and machine learning. And
so sorry to interrupt, but I mean, it's just really interesting contrast there or complementary sets of skills like around between operations research and machine learning and applied machine learning and artificial intelligence.
Mhm.
So I'm sort of curious how, how much AI and ML was there in that operations research course that you did?
At the time, it was largely electives. Now I think more and more it's integral.
Yeah.
Um, Absolutely, especially with, and this is going off on a little bit of a tangent, but especially things like reinforcement learning, right, play very nicely into uh, traditional problems that operations research analysts might work on. But yeah, I think that there's really neat synergies behind what folks in operations research more traditionally would work on and applications for machine learning. One of the things that I was especially interested in is how do we apply machine learning to boost strategies for predictive maintenance on, say, wind turbines, right, or other generating assets. And that was something that I was even starting to get interested in grad school, and then joining Nexterra, that was a tremendous learning experience, right? Seeing how this is done in the real world, right, at scale, and being able to learn from a lot of the fantastic experts in their field there.
Yeah, that's well, yeah, and it's like that real world experience working for a network operator, which gives really sharpens up those those things that you learned in class. So, in
Mhm.
fact, I think we're probably going to jump into some of that stuff now because one of the main reasons I really wanted to get Aaron on and to talk with Aaron was because of these use cases that we were talking about. We got into this great discussion about fault prediction, preventive maintenance scheduling as really critical and interesting use cases for electricity grid operators. And I wanted to get you on here and to share some of your insights into that area. So, I mean, why is this such a key area or such a critical use case for grid operators?
Yeah, it's very high impact, right? Especially because grid operators, you know, uh, they're largely evaluated by their ability to deliver at a high service level, right? In a very literal sense, right? Regulators are looking at metrics like SAIDI, SAIFI, right? Outage rates, availability, and at a more abstract level, right, or a more qualitative level, customer satisfaction is critical, right? Especially for regulated utilities, right, where it's important to have buy-in from the public, right, as an electricity monopoly, right? So, and then for example, independent power producers, right, profitability is directly tied to uptime, right? Not just in terms of revenue, but also penalties for defaulting on obligations, right? Reliability is paramount here. There's a lot of neat applications here at different levels of abstraction, right? From individual devices on the distribution grid, for example, and how reliable are those, right? Are they operating as expected, to much more abstract problems of if you're not predicting individual failures, say on the distribution or transmission grid, but more like statistical likelihoods, and where do you stage technicians and other resources for rapid response, knowing that certain regions may have a different propensity for a different kind of failure than other regions, right? And how do you allocate staff on a more macro level?
Yeah.
So there's lots of different dimensions and levels of scale at which you can work on these problems.
Yeah, and
Um,
maybe not even just what staff you have, but potentially, I suppose, also what parts or what spares you have on hand to be able to handle those particular things that you're more likely to come across.
Huge problem and very valuable problem. right? One of the things, especially with transmission distribution, is not just the tooling, but the spare parts and the assets are fantastically expensive, right?
Yeah.
And to replace an asset that has failed unpredictably is incredibly expensive, right?
Yeah. Well,
And it's not
that
just
gets onto
yeah, not just
yeah.
catastrophic failures, but also the cost of say a false positive. If you're predicting that something is going to fail within a near time frame, right? You inspect it, and it turns out there's a false positive. A lot of these failure modes can't be verified non-destructively, right? You have to open up the transformer and um, and compromise its integrity, right, in order to verify, hey, this thing degraded in a particular way, and that's no good either, right? So having a very low false positive rate and a very low false negative rate is paramount when you're dealing with
Yeah.
assets
So
that are, yeah.
what are some of the consequences of false negatives, right? I mean, so we just talked about the false positive stuff, but
Mm-hmm.
I hadn't, until we talked the other day, I hadn't thought that much about the false negative case. But what's the cost of false negatives in that sort of scenario?
Yeah, absolutely. I think the most, especially for let's let's limit it to like electricity distribution and transmission, right? I mean, immediately unplanned outages are pretty terrible for consumers, for commercial and industrial customers, right? And to have to restore electricity quickly on demand. You mentioned one of the key things that we might have to worry about at a grid operator is, are your replacement parts sited and sourced where you need them to be, right? Well, if you have to deliver replacement assets at the last minute, right, in order to minimize the harm to your reliability metrics, right, that can get ruinously expensive as well,
Yeah.
right? So being able to have lead time or advance notice can represent substantial operating savings.
And why do you think it is that we're seeing such a big increase recently, the last year or two, in the role of machine learning in these grid fault prediction use cases?
I think a lot of it's driven by the fact that we have so much data availability now that past generations of reliability engineers, um, yeah, more like in the past few decades, didn't have, right? Especially when ensembling lots of different data sources from different devices, right? And the continuing rollout of the smart grid, right, especially in North America, is empowering this. When I started in 2016 at Nexterra, right, smart grid device rollout and integration was progressing pretty steadily, but hadn't, there were some regions that penetration was pretty high and some regions that barely started. And now in 2024, there's just so much more data availability for grid operators and asset managers. It's phenomenal, right? There's a
Yeah.
lot to work
Well,
with.
like the smart grid penetrations definitely increased a lot over that time.
Yeah, the promise is becoming fulfilled, right? And there's just such an opportunity in a way that, back in the 1990s or the early 2000s, right? A lot of this would have been, well, science fiction. And especially with deep learning and other approaches that require big data sets, right? It just wasn't practical before now. Especially if we look at, on the more granular level, a lot of the work that's being done on, let's say, analyzing waveforms, right, for patterns that might predict incipient faults, right? A lot of that wasn't really practical outside of a laboratory setting until not that long ago. And even when I had started Nexterra, there was already a renaissance in research around that at scale. So it's a very exciting time to get started in that. And related to that, I think one of the things that makes machine learning applications especially interesting here is, especially when you're working at scale, a lot of these more complex faults, right, are not necessarily reproducible in the lab, right, on a test bench. I think a lot of times for strange edge cases, right, that are still incredibly important to understand and to model, these come out of system complexity that you have to be collecting field data for. And
Makes
it doesn't
sense.
lend itself well to test
Yeah,
bench testing.
right. So, I mean, okay, so on the positive side, there's obviously a lot more data. So a lot more historical data, that you can, that you can train on, and you can, analyze for patterns and all that sort of good stuff. A lot more potential real-time, data access. A lot of these devices are just throwing off data like constantly. So what would then come down on the sort of problem or challenge side? So when, let's say, you're trying to apply machine learning techniques to this fault prediction and predictive maintenance scheduling problem, what are the challenges from a data science point of view that you have to overcome?
Oh, this is my favorite part, James. I think one of the things that is fascinating about fault detection and reliability modeling is what we would call heavily imbalanced data sets, right? Fortunately, for most grid operators, a lot of these faults that we're trying to detect are very rare, right? And this is a good thing for electricity users and customers of utilities and those that benefit from asset reliability. But it also means that building training sets that have enough cases to draw inferences is challenging. It's these imbalanced data sets mean that a lot of techniques that are used in other machine learning domains don't apply as well. And a lot of techniques that are used to correct for imbalanced data sets, like, for example, in machine vision, right? Traditionally, there's been a lot of interesting work on how do you augment images, right, and transform them in certain ways.
Yeah, rotate them
Your,
and like scale them up and down and all that sort of stuff. Yeah.
exactly. And with a lot of these, with a lot of these applications in reliability modeling, it doesn't work quite that way, right? So there's some techniques that are available to us and other ones that are less applicable.
Yeah.
But that makes
So
it really challenging.
yeah. Well, that does make it pretty interesting, right? So as you've said, I mean, imbalanced data sets are not a new thing, right? Like there are a lot of areas out there that have had to handle this. Like, the medical field has been one that's had to deal with this a lot. And some of the cybersecurity use cases are very, heavily imbalanced. So what have you found that some of the techniques and algorithms would be that you would recommend that have proven to be applicable in this sort of problem, like around fault detection?
Yeah, absolutely. So one of the papers that's actually had a really strong influence on how I approach these problems personally. I came across this back in, I think, 2016 or 2017. There's actually a master's thesis from 2015 that I came across a blog post by the gentleman who wrote it, Egil Martinson. And he originally wrote this in the context of detecting customer churn for, I think it was e-commerce, right?
Yeah.
And this was a paper that had a strong impact on me because the punchline effectively was, how do you reframe the problem that you're looking at in order to make it tractable? Where traditionally, when I started, a lot of common approaches came down to, can we predict if this particular device is going to have a fault in the next N days, right? Or are we going to have an outage or a failure in some window of time binary classification, yes or no, what's your probability of that? And one of the things I was fascinated about this paper is it very elegantly reframed the problem as, can we instead predict the time until failure, right? Which is not that new a thing, but it walked through how do you take the learnings from the literature on time to failure modeling and reformulate them in a way that you could apply them to machine learning models, and in particular deep learning models, right? Specifically recurrent neural networks, right? How do you take that learning and build a loss function, right? When we're talking about training machine learning models, right? How do you construct a loss function that represents time to failure when you have what's called censored data, right? And this is what gets to the rare event, right? The imbalanced dataset piece is that you may not have that many examples of cases where your asset or an asset like it has failed in the past. But every day that your asset has not failed yet in your training data set, right, tells you some evidence, right? It tells you under these conditions, I have such and such amount of time before my asset will fail. But if your asset hasn't failed yet, right, by the time you stopped collecting your data, right, that also gives you evidence that says, I don't know when it's going to fail in the future, but I know it at least isn't until today. And that's also evidence that you don't want to throw out. You can take advantage of that when you're training a model predicting time to failure. And that paper in particular, it was something that really opened my eyes to how you can elegantly express these ideas, right, and recast them in a way that becomes amenable to throwing all these interesting algorithms at them. So I would say, reframing things in terms of time to failure in a way that you can apply machine learning techniques to it opens up a lot.
And that sort of gets back to a little bit to the medical sort of field, right? Where a lot of the algorithms for this survival analysis originally did come from survival analysis of cohorts taking part in clinical trials and things like that. And so, yeah, it's really, I think, exciting to be able to apply those techniques to, to different domains like asset lifetimes and things like that.
That's a really good point. Yeah, a lot of this has, so to speak, its DNA in, public health statistics and actuarial tables, right? And a lot of the really pioneering stuff that was done in the 20th century, right? With, like you said, literally survival analysis.
Yeah, that's right. So then, if we sort of cast our eyes a bit into the future, what do you see as being some of the things on the horizon as far as AI and ML and fault prediction on the grid?
Sure. So I've got two answers for you on that. One is, I think, a little bit more conventional wisdom, but still, I'm still feeling pretty confident in that. And the other one, I think, as a practitioner, is really interesting and maybe not quite as talked about. We hear a lot about increasingly moving inference to the edge, right? And that's been the case for a while, especially with things like waveform analysis, right? That a lot of the computing and the use of these models to make predictions and inferences it's increasingly going to be done on smart devices that are deployed in the field rather than in the cloud, right? Or at a centralized data center. And I think that's going to continue to happen. And what I think is going to continue to develop is the sophistication of what's done at the edge, right? Especially with devices on the edge, deployed in the field, talking to each other, right? And predicting and faults more autonomously, right? Especially because, um, especially with a lot of high frequency data, right? The latency sending data back to the cloud and back again matters, right?
Yeah.
So the more that can be done on the edge, I think the more responsive a lot of this analytics is going to be, especially when we're talking about, say, self-healing devices, right, in the
Yep.
distribution grid. I think the other thing that I'm keeping my eye on, especially as a practitioner, is transfer learning from other domains. And what do I mean by that? For example, when we saw a lot of really path-breaking research in machine vision, object detection, things like that, um, with a lot of the deep neural networks that were being used for machine vision models, right? Earlier layers, for example, like earlier convolutional layers in these networks were often picking up more abstract features in the image, right? And as you go deeper in the stack, you should be refined into more symbolic ones, I guess, if you're going to interpret it that way, right? Moving from things like lines and edges and rough shapes and colors to, look, this layer is very good at picking out things that are animal-like in nature. And what would often happen with this sort of transfer learning is you would see when folks would develop new models, they might take the pre-trained weights from earlier layers, right, in some other group's model and stack them on top um, of the architecture that they were developing, right, and then train just the very end of the stack, right? So we're going to take advantage of work that's already been laboriously done on fitting weights for picking out edge features and shape features and things like that, and just refine the latter parts, right? And I think we may see something similar with actually borrowing a lot, potentially even from sequence to sequence models like natural language processing models, right? Not
Oh,
necessarily that, say what's being trained for LLMs is going to port over easily, right? But I think with a lot of work that's being done on sequence to sequence models, like for natural language processing, right? Training architectures that are able to efficiently pick out patterns in sequences of data. I think we might be surprised to see how much of that is cross-applicable, even if it doesn't seem obvious, right?
yeah. And sound like just a really rich area for experimentation, right? That's the fun part of it, is working out which of those pre-trained models may have some really useful weights already, already.
Mm.
Uh, so look, I really appreciate it, Aaron. Let's wrap it up there. This has been really interesting. Thank you for joining me today and sharing your insights about this really interesting area. There's two things that are very close to my heart: energy and AI and ML. So it's been really fun to spend time with you on that. And thanks to everyone for joining us on the Coffee Chats about AI podcast. And we will see you next time.